Have you ever played a game on your phone or computer and wondered how it all works? How does a digital car know how to drift around a corner? How does a thrown ball arc through the air and bounce off the ground? It all feels like magic, but it's actually something you can build yourself. We're talking about physics simulations, and you can create them right inside a web browser using just JavaScript. This isn't just for games either. Imagine an online store where you can pick up a product and turn it around, or a website that teaches you about the solar system by letting you fly a spaceship between planets. That's the power of 3D physics on the web. It turns a flat, boring page into an interactive world that grabs your attention and doesn't let go. The best part? You don't need a bunch of fancy, complicated libraries to get started. Many tutorials will tell you to download this or install that, but we're going back to basics. We're going to build our own tiny physics engine from scratch. Why? Because when you build it yourself, you understand every single piece of the puzzle. It's like learning how an engine works by taking it apart and putting it back together. You'll see exactly how we can trick the computer into making objects behave like they do in the real world. This approach gives you complete control and a much deeper understanding of how these incredible digital experiences are made. It's a fun challenge, and the skills you learn are super valuable for any web project. Creating these simulations is all about breaking down big problems into small, manageable steps. We're not going to build a blockbuster game overnight. Instead, we'll start with the fundamentals. Think of it like learning to cook. You don't start with a 5-course meal. You start by learning how to boil water and chop an onion. In our case, we'll begin by defining what an object is in our 3D space. Then we'll figure out how to make it move. After that, we'll introduce forces like gravity to influence its movement. Step by step, we'll add layers of complexity until we have something that looks and feels alive. It's a creative process that blends logic, math, and a little bit of imagination. This journey is for anyone who's curious and wants to make cool stuff for the web. You don't need to be a math genius or a coding expert. If you have some basic JavaScript knowledge and a passion for building things, you're ready to go. We're going to keep the concept simple and the code easy to follow. By the end, you'll not only understand the core principles of 3D physics, but you'll also have the confidence to start experimenting on your own. So, get ready to roll up your sleeves and build your very own pocket universe. It's going to be a blast, and you might just surprise yourself with what you can create with just a few lines of code. Before we can write any code, we need to understand the 3 core ideas behind any physics simulation. These are the rules of our digital world. The first and most important idea is the object. In our 3D world, an object is anything that has a position, a size, and a way to move. Think of it as a digital bowling ball or a bouncy rubber ball. For our simple simulation, we can represent an object with a few key properties: its x, y, and z coordinates to know where it is, and its velocity to know where it's going. The velocity is also broken down into x, y, and z components, telling us how fast it's moving along each axis. It's like giving our object a starting point and a direction to travel. Next up, we have forces. An object sitting still won't do anything interesting on its own. Forces are the invisible hands that push and pull on our objects, making them move in realistic ways. The most famous force, of course, is gravity. It's the constant downward pull that makes an apple fall from a tree or a thrown ball arc back to the ground. But forces can be anything. A gust of wind could be a force that pushes objects to the side. The thrust from a rocket engine is a force that pushes a spaceship forward. In our code, we'll represent forces as an acceleration, a change in velocity over time. By applying forces, we can make our objects speed up, slow down, or change direction. Finally, we have the most exciting part: collisions. Our 3D world would be pretty boring if objects just passed right through each other like ghosts. Collisions are what make the world feel solid and real. When 2 objects collide, they need to react. A ball hitting a wall should bounce off it. 2 billiard balls striking each other should fly off in different directions. Handling collisions involves 2 steps. First, we need to detect when 2 objects are overlapping. This is called collision detection. For simple shapes like spheres, this is pretty easy. We just check if the distance between their centers is less than the sum of their radii. Once we detect a collision, we need to make the objects respond realistically. This is called collision response. This is where we change the object's velocities to make them bounce away from each other. For example, if a ball hits a flat floor, we can simply reverse its vertical velocity to make it bounce back up. If 2 balls hit each other, the math gets a little more complex, but the principle is the same. We calculate their new directions and speeds based on the angle of impact. These three concepts, objects, forces, and collisions, are the fundamental pillars that will support our entire 3D physics simulation. Master these, and you can build almost any interactive world you can imagine. Now for the fun part, let's translate these ideas into actual JavaScript. First, we need a way to represent our 3D objects. A simple JavaScript object is perfect for this. We can create a blueprint for a particle that holds all the information we need. It will have a position, a velocity, and maybe even a radius. Think of it like a character sheet for our digital actor. The position will have X, Y, and Z values, and so will the velocity. We can also add a property for acceleration to keep track of the forces acting on our particle. It might look something like this. Let particle equals position x0, y100 z0, velocity x5, y0 z0, radius 10. Now we have a digital ball ready to go. To make our world come alive, we need a game loop. This is the heartbeat of our simulation. The loop runs over and over again, many times per second. In each tick of the loop, we update the state of our world. We'll use a JavaScript function called requestAnimationFrame to create a smooth and efficient loop that syncs with the browser's refresh rate. Inside this loop, we do three things in order. First, we apply forces. Second, we update the positions of all our objects based on their velocities. Third, we check for and handle any collisions. This cycle, apply forces, move, check collisions, repeats continuously, creating the illusion of smooth, real-time motion. Let's look at a simple code example for applying gravity and updating an object's position. Inside our loop, for each particle we first apply the force of gravity. Gravity is a constant downward acceleration, so we'll just subtract a small value from the particle's y velocity on every frame. Something like particle velocity y minus equals 0.1. Next, we update the particle's position based on its current velocity. This is as simple as adding the velocity to the position. Particle position x plus equals particle velocity x, particle position y plus equals particle velocity y, and particle position z plus equals particle velocity z. Just these few lines of code, running inside a loop, will make our object arc through the air like a thrown ball. Now let's add a simple collision. We can create a floor in our world at y equals 0. To check for a collision, we see if the particle's I position has dropped below the floor level, taking its radius into account. Particle position y minus particle radius less than 0. If it has, we need to respond. A simple response is to reverse its y velocity to make it bounce. We can also reduce the velocity slightly to simulate a loss of energy, making the bounce less high each time. Particle velocity y times equals negative 0.8. We also need to make sure the particle is placed back on top of the floor so it doesn't get stuck. With just this logic, you now have a bouncing ball simulation built entirely from scratch. As you start adding more objects to your simulation, you might notice things begin to slow down. Keeping your physics simulation running smoothly, even with dozens or hundreds of objects, is a big challenge. This is all about optimization. One of the biggest performance killers is collision detection. If you have 100 objects, checking every object against every other object is nearly 5,000 checks on every single frame. That's a lot of work for the browser. A smarter way to handle this is to use a technique called spatial partitioning. Imagine dividing your 3D space into a grid. Now, you only need to check for collisions between objects that are in the same or neighboring grid cells. This dramatically reduces the number of checks you need to perform. Another key to a smooth experience is using a time-based update loop. Sometimes a computer might be running slow, and your requestAnimationFrame loop might not run as often. If your movement is based on frames, your objects will move slower on slow computers and faster on fast ones. That's not good. To fix this, we calculate the time that has passed since the last frame. We call this delta time. Then, we multiply all our movements by this delta time. For example, position x plus equals velocity x times delta time. This ensures that your simulation runs at the same speed on all devices, regardless of the frame rate. It's a crucial step for creating a consistent and fair experience for everyone. Now that you have the basic building blocks, the real fun begins. The world is your oyster. You can start experimenting. What happens if you add a force that constantly pushes objects to the side? Try creating different kinds of objects. You can make some objects static, like walls, that don't move at all. You can give other objects different masses so that when they collide, the heavier object is less affected. You could even simulate springs by creating a force that pulls two objects together, or pushes them apart if they get too close. Each small change you make can lead to fascinating and unexpected behaviors in your digital world. The goal here isn't to build a perfect, bug-free physics engine on your first try. The goal is to learn and to have fun. Building things from scratch gives you a superpower: the ability to understand and control every aspect of your creation. Don't be afraid to break things. Every error message is a learning opportunity. Start small with a single bouncing ball, then add another, then add walls. Keep building, keep experimenting, and keep asking what if. You'll be amazed at the complex and beautiful simulations you can create with nothing more than a text editor and your own imagination. Go ahead, open up a blank file, and start building your universe.